Start with you.
Number 22.
22 from, you're in 5-1?
Oh, yeah.
Okay.
Can I interest you in some chips and salsa? I'm all set. Yes.
All right. So it says on 22, determine a region whose area is equal to the given limit. Do not evaluate the limit. So basically what we want to do is we want to figure out, like, what is this picture equivalent? Or what picture, like what function area under the curve is this equivalent to? Okay? So, like, remember we did, like, you had some f of x, and you had, like, from, like, area under the curve from, like, A to B. It's trying to figure out what area is that essentially equivalent to, right? So that's what the question is asking. Does that feel okay so far? Okay. So what I want to remember here is that in 5-1, let's find the exact thing I'm looking for so you can see what I'm doing. Let's see. Okay, so basically what we're saying, where are we? Yeah, so this is what I'm looking at. So I know that my area is equal to the limit as n approaches infinity of 2 over n, or I'm sorry, of, I gotta write it down, f of xi star delta x. And I remember that delta x is equal to b minus a over n. And I remember that xi is a plus I delta x. Or in our case, so let's kind of identify what's going on here. So the delta x in our case looks like it's 2 over n. Okay. And if I look here, then at this case, this looks like my I times delta x, right? Because that's 2i times delta, or 2i over n. So we can say that xi is going to be 5 plus 2i over n. And I'll write it this way. So, like, here's my delta x. So this part right here must be my a. Does that feel okay? So if I know that 2 is equal to b minus a, and I know that a is 5, I can say here that b has to be 7. Okay? So this is the area under f of x equals, now if I look at my function here, that's going to be the whole thing, right? So this, what I'm looking at is like xi to the 10th. So this is just, my function is just f of x to the 10th. Do you see that?
Yeah.
Okay. From a equals 5 to b equals 7. So it's just kind of about decoding what it is that you're looking at, right? Like, where's the delta x? Where's the xi? That's going to give me my a and my like what I need, and then like I just look at the form of the function that I'm taking the sum of, and that kind of gives me my f of x. And it's not hard once you see what to do, but like looking at it the first time, it's like, what am I supposed to do with this, or what is this even asking? Right? Like the vocabulary is difficult,
That makes sense.
but that's the idea. Is that okay?
Oh, yeah.
Okay. Elena, you said you had one. 24. Okay. Hi, Isabel. So it says use definition 2. Let's go back and look at what definition 2 was. I'm probably going to have to look at it here. There's 1. Oh, there's 2. Okay. So I'm going to just drop in definition 2 here for us. Is that okay? So we can look at that as we're going. Hi, Giselle. So it says use definition 2 to find an expression for the area under the curve y equals x cubed from 0 to 1 as a limit. Okay, well, I know the area is going to be the limit as n goes to infinity of, we're going to need to calculate a delta x. So again, that's going to be b minus a over n. Oops. Come on. Or 1 over n. And then I'm going to write this as the sum I equals 1 to n of f of xi. Now the xi in our case is going to be a plus delta x times I, or just I over n. And our f of x in this case is told us in our function is y equals x cubed. So we'll say that's going to be the limit as n goes to infinity of 1 over n sum I equals 1 to n of I over n cubed. So that's my part A. Elaine, are you okay with what I did there?
For the epsilon, how do we find that again?
So this is a formula. A plus I delta x. And our A was 0, right? Because we're told we're going from 0 to 1. So that's my A and B. And y equals x cubed is my f of x. And so I'm just kind of filling in my formula now. Does that feel okay? And if you want to write that sum as an expanded thing, you don't have to write it with summation notation like I did here. It just means more writing, but you're free to write like, 1 over n times, like 1 over 0 plus 1 over n to the third plus 1 over n times 0 plus 2n over, or 2 over n to the third plus ... You know what I'm saying? You could write it that way also. That's fine. No penalty there. I just typoed. It's supposed to be infinity. Thank you.
Yeah.
Good question. It would make no sense if n is going to 0. Jacob.
I do have a question. Where's the I over n come from? Like, I know it's representing x.
So remember delta x is 1 over n.
Okay. Yeah.
times I and then plus 0. So just I over n.
Gotcha.
So that's just the xi.
Okay.
Okay, let's look at part B now, which is probably the more challenging piece. It says the following formula for the sum of cubes of the first n integers is provided in appendix E. Use it to evaluate the limit in part A, and it tells us what that formula is. So we have the limit as n goes to infinity of 1 over n times the sum I equals 1 to n of I cubed over, I over n cubed. Right, that was our formula that we wrote earlier. So what I'm going to do is I know that if I have the exponent of a fraction, that's the same thing as the numerator cubed over the denominator cubed. And now these 1 over n doesn't contain an I in it. So I'm going to pull that out front of my, outside of my summation and combine it with the 1 over n out front there. To get that. Is everybody okay to see what I did there? Now I'm going to use the formula that they gave me in the problem. So they told me that the sum of I cubed is just that. So I'm going to make a substitution now where I'm going to replace this with that quantity n times n plus 1 over 2 squared. So far, so good. So I noticed that if I have, again, this is just a fraction squared, right? So that's the same thing as the square of the numerator and the square of the denominator. And that numerator is a product. And I know the sum, or a product squared is just going to be the factor squared. And I'm going to stop and think about what I have here. So what I really have is something that looks like this, right? What kind of function is the numerator? N times n plus, or n squared times n plus 1 squared. What is that? Well, it's not quadratic because it's going to be degree 4, but it's a polynomial, right? What's the denominator function? Polynomial. So what I have is the limit of a polynomial over a polynomial. We know how to do that. What does it depend on? The degree of the numerator and the degree of the denominator, right? What's the degree of the numerator? No. 4, because I have n squared times another n squared. So it'll be n to the 4th. What is the leading coefficient on that n to the 4th term? 1. What's the degree of the denominator? 4. What's the leading coefficient in the denominator? 4. So what should this limit be? 1/4. Done. Now you could have foiled things out in L'Hopital and you could do all that, but we've done this problem. We know the shortcut. Let's not pretend like we don't. Is everybody okay with what we did there? Now, better than it looked, right? It started to look pretty nasty, but the limit turned out to be something that was pretty easy to do. Beck.
So what is that? Is that approximation of area, or is that?
That is the actual area. That is the area, because we've taken n going to infinity. So that's infinitely many rectangles we've used now. So it is the exact area. Rita.
It's like, why do you say like I equals 1? Like, what is that actually? Like, I look it up.
Okay. So if I take this, this is the same thing as saying, starting at 1, having 1 cubed, and then 2 cubed, and then 3 cubed, all the way out until we get to n cubed.
It's like I just starting.
I is like the index value, or the index variable for the sum. And what I equals is the value that your summation starts with. So we're starting by plugging 1 into the function that we're summing. And it ends at the top at n. Yeah, almost always it'll be I equals 1 to n. In fact, with what we're doing right now, it's always going to be I equals 1 to n. If you're doing, like another class, sure, the odds could be other things. But like what we're doing with these sums is that. Does that make sense?
Yeah.
So again, all this summation is a way to compact writing this. Which again, like you don't have to use the summation symbols. You can just write like the sums with an ellipsis. It's a lot of writing. Doesn't matter, easy, it's quicker. Doesn't make it easier, but because it's another layer of notation to fight through, but that's all it's saying. You guys feel okay about the homework otherwise? Should we start 5-1? Or I'm sorry, 5-2, I should say.
Would you give us something like what we just did 24?
You'll be doing that again in 5-2. So we'll see this idea in 5-2 again, and you'll get much more comfortable with it after doing it a couple of times. And we'll do some examples here in the 5-2 notes. So the answer to your question is yes, you'll see that process again because we're literally going to be doing it in 5-2, and then we're never going to do it again when we get to 5-3, because we're going to look at like, oh, that's a much easier way of doing it. Just like when you use the limit definition for a derivative, it's like, oh, okay, I have to do that every time, huh?
Right.
No, we had to do the definition, and we never do it again. So it's kind of this, at least until you want to try to prove something or whatever, but it's kind of it's very much the same way. Does that feel okay? Okay. So we're going to start with the definition. So we say that f is a function defined from a to b. We divide that interval from a to b into n subintervals of equal width, that we'll call that equal width delta x, and that equal width will be calculated by b minus a over n. Everything exactly the same as what we saw in 5-1. We let x0 be equal to a, the very first value in our interval. And then x1, x2, x3, all the way out to xn, which is equal to b, the last value in our interval. And those are going to be the endpoints of the subintervals. We let x1 star, x2 star, all the way out to xn star be sample points in these subintervals. That means that for some x sub I, that's any x value between x sub I minus 1 and x sub I. So if we had like, let's say x sub I is the interval from 2 to 3. X sub I star is any value between 2 and 3, including 2 and 3. So it could be 2.1, could be 2.9999, could be 3, could be 2.16. Doesn't matter. It's just some value in that interval. Is everybody okay with the notation there? Okay. we say then the definite integral of f from a to b is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x of x, f of xi star times delta x. And we know that this is our area under the curve of f of x from a to b. Provided that this limit exists and gives the same value for all possible choices of sample points. If that's not the case, or if that is the case, we say that f is integrable on a to b. So that means that there is an area, right? You can find the area on that interval. So this symbol here is our integration symbol. So this is supposed to look like a little bit like a stretched letter S. Why do you suppose it looks like a stretched letter S? S is for sum, because that's what we're doing is we're adding things up. We're taking a sum. The A and B is the start and end of our interval that we're finding the area under. And the dx is really just part of that integral symbol. You can think about that as like the start and the dx is like the end. We'll talk more about like what the dx means in like theoretically later, but for now just think about that as like the S symbol is like your start of your integral and the dx is the end of what you're integrating. And you can think about it that way. Does that feel okay? So just from a notation standpoint, a little vocab. So that integral symbol is called the integral sign. The f of x inside our integral is called the integrand. So that's the function that we're integrating. The a and b are called our limits of integration, where the a is the lower limit and the b is the upper limit. And the process of actually doing this calculation is called integration. Okay, so integrable means that we can find that area. Integration is the process of finding the area. The integrand is the function that we're going to be integrating. The limits of integration is the start and end of the interval that we're finding the area of. Does everybody feel okay with the vocabulary? Okay, I know that was a lot of terms just thrown all bleh. And if I say something and you're not sure what it meant, feel free to ask again and I'll be happy to reiterate what those things mean. Okay. So important conceptual piece here. The definite integral from a to b of f of x dx is just a number. This whole thing represents an area under a curve. It's a number. It does not depend on x. So the letter that you use is irrelevant. You could say the integral from f of x, or from a to b of f of x dx, or you could say the integral from a to b of f of t dt, or you could say the integral from a to b of f of r dr. It does not matter. They should give you all the exact same value because the letter, or this is just a number, and the letter name, the name of the variable is just a name. Doesn't matter for a definite integral. Okay. So this sum that we're adding up, these rectangles, right? That's really what this is. This is a bunch of adding up the areas of a bunch of rectangles. Has a name. We call this a Riemann sum. The AP will use that specific terminology. So they'll say, like, approximate this integral using, 6 Riemann sums with left endpoints or something like that. So it's basically asking you to calculate like L6. Does Is everybody okay with that? So that term Riemann sum is just adding up rectangles. Yes? Okay. Again, Bernard Riemann is a German mathematician that's named after him. So again, example, figure 1 is a bunch of Riemann sums. That's going to be an approximation for that integral. Figure 2 is the actual value for the integral. So Riemann sum is going to be an approximation of the integral, and the actual process of integrating will give you the actual area. That's going to be possibly a different number. So the key with a Riemann sum is that it's finite, right? You're adding up a finite number of rectangles. When you do the integral, then you're taking the limit as that number of rectangles goes to infinity. That's going to give you the actual area. So that's the difference between the two. Everybody's okay? Okay. Again, if I'm going too fast or you're not sure or you want to ask about something, please say something and I can stop and we can do some more. We can draw some pictures. We can do some specific example. But right now it's just like kind of some theory, right? So there's not a lot to practice yet. Okay, so what happens if f takes on both positive and negative values? So like what we're seeing down here for this function, where it dips below the x-axis and for part of it, and part of it's above the x-axis. So in that case, the Riemann sums of the rectangles that lie above the x-axis would be positive, and the rectangles that lie below the x-axis would be negative. So in the case, you might end up with negative area under the curve. That's okay. You can end up with 0 area under the curve if you have the same amount above as you do below. That's okay. Generally, what you would do in that case is you would like break this into like 3 integrals and do them each separately and then just like add up the result. Like you could do it that way. But that's the idea. So again, you can have negative area provided the Riemann sum for that rectangle is below the x-axis, or the rectangle representing that part of the Riemann sum is below the x-axis. Everybody's okay? When we see how to do this like the shortcut way, it doesn't even matter. Okay. All right. So we've defined what we mean by a definite integral for an integrable function, but not all functions are integrable. You cannot integrate every single function. Well, I think I asked you actually to do one of these problems, 69 or 70, I can't remember. I think one of them is in the homework set. The following theorem shows that most commonly occurring functions are in fact integrable, and you wouldn't prove this theorem in an undergraduate course. This is probably like a real analysis kind of problem. But you would say, or the theorem states that if f is continuous on AB, or has only a finite number of jump discontinuities on AB, then f is integrable on AB. So, for example, if you wanted to look at like a step function, where it goes like something like that, we can still find the area under that curve. That's fine. Because how many jump discontinuities do I have here? 4, finite number, right? Now, say we have a jump at every like irrational number between A and B. How many irrational numbers are there between A and B? Infinitely many. Can we integrate that? No way, Jose. Everybody's okay? All right. So that's, I think, even the answer that you're looking for that question later on, or the key to that question later on that I said was probably in the homeworks, that I think was in the homework set. If f is integrable on AB, then the limit in definition 2 exists and gives the same value no matter how you choose your sample points. To simplify the calculation of an integral, we often take the sample points to just be the right endpoints. Then xi star just becomes xi, and the definition from definition 2 for an integral just becomes that same limit of a sum that we looked at in 5.1. Does everybody feel okay there? All right. Let's do some, we have, an example. So it says, express the limit as n approaches infinity from I equals 1 to n of the function x sub I cubed plus x sub I times sine of x sub I delta x as an integral on the interval from 0 to pi. Now, it's not asking us to calculate the area under this curve or to find the value of the integral. It just wants us to write it as an integration problem. So if it's going to be an integration problem, we're going to start with our integration symbol. What are the limits of integration for this problem? Zero to pi. Everybody's okay there? What is the function that we're integrating? This thing, right? With the one exception, should we be writing xi's? No. What should we be writing? Just x. Isabel? Well, the I is just the index for the sum. We're not doing a sum anymore. It's an integral, so no subscript is necessary. And then what do we need to say that we're done with our integral? A dx at the end. And that's it. We did it. So all it wanted us to do was to go from this to that. That's easy, right? Not a big deal. Okay, I left a lot of space. All right. So, summation formulas. If we're actually going to be calculating an integral from our definition of an integral, we'll be using these three summation formulas in addition to some other ones, but these will be our primary tools. So this is something that is in your textbook, but you'll use this throughout your homework. These three formulas you'll use throughout your homework today. So far, so good? Do you need me to pause for a minute? Are we copying these down? I can pause. Yeah. How's this feel so far? Is this okay? Again, like, the hope is the way we've constructed the course is things are feel more familiar, the notation's not as hard, the concepts become more familiar feeling, where this idea of like we're just doing infinitely many things is no longer a foreign concept. It's something we've done, use this idea of like infinitely close, should feel pretty familiar. Okay. And then we have these others that I would call minor sum formulas, But let's look at essentially what it's saying here. So C is a constant, right? If I add up n C's, how many should I have? N times C of them, right? That's all that's saying. Here it's saying that if I have a constant times a function, I can just pull the constant out front. We've been doing that already. If I have the sum of two functions that are being added or subtracted, well, I can just take the sum of each function individually and then add or subtract those sums. Which is, again, all we're saying is we can distribute that summation symbol. Right? So those are like I would call minor. These are more like rules of things you can do with your sum. And again, these will be the tools that we'll be using to actually compute our integrals in this section. In the next section, we see there's an easier way. But, you know, it was a big breakthrough because the title of the next section is The Fundamental Theorem of Calculus, which, as you imagine, is rather important. And that's our main tool here. All right. So let's do some actual numeric computational example now. Right? We've kind of gone through the theoretical pieces. Let's do this. So part A says evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be right endpoints, and a to be 0, b to be 3, and n to be 6. So basically, we just want to calculate R6, right? So our delta x is going to be b minus a over n. So that's the width for each of the rectangles. And then the point at which we're going to evaluate each of the rectangles, oops. And at this point, you can kind of probably see the pattern of what's going on here, right? What should x6 be? Should just be the b, right? Should be the end. Is that okay that I didn't write them all out? So this is going to be f of x1 plus f of x2 all the way out to plus f of x6. Is everybody okay with that? At this point, it's going to be calculator time for me. I'd invite you to take out your graphing calculator with me as I show you the shortcut ways to do this. I'm going to begin by pressing the y equals button. I'm going to clear out my y equals menu. And where y1 is, I'm going to type in the f of x for this problem. So that's x cubed minus 6x so far so good. I'm going to exit out now, pressing second in mode. I'm going to go here and make sure that my calculator is in radian mode. I'm not sure what the approximation program is that's, or like the code for the approximation program we're about to use is, but I suspect being in degree might have an impact. I'm not positive, but I know that it wouldn't if it's in radian, so I'm just going to put it in radian. So now I'm going to do this R6. I'm going to do it all at once. So I'm going to do 1/2 times. And now I'm not going to type in y1 of 1/2 plus blah, 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 blah. Okay? I'm going to do the following. I'm going to press the math button, and I'm going to scroll down till I find the summation command. So now I have this nice little summation symbol. Notice there's a bunch of blanks that I get to fill in. So the first blank is going to be the variable name that I'm going to use. I'm just going to use X. You could use I if you wanted to, or whatever letter, but like I'm just going to use X because it's on there. We're going to start by going to 1 and then ending at 6. And now I need to type in my value, but here really I want X sub I that's I times delta X, or I over 2, right? Everybody's okay with that? Okay, so go back to this. And so now with my function, I'm going to have X sub I, which in our case is I over 2, which is in our calculator, it's going to be X over 2. So I'm going to do quantity X over 2, and then cubed, and then minus 6 times X over 2. And I'll press enter. Is that what you guys all got?
The last thing you do, like minus
6 times X over 2, right? All the X's are Xi's, so it's going to be I over 2, or X over 2 in our case. Notice if then the question asks you to do this like with 12 subdivisions instead of 6, all that you would need to do is update one number, right? All we need to do is update this. Oh, I'm so dumb. Here, this would have been a better way of doing it. We could have just done this as vars y1 of X over 2. That's way less typing, right? Mr. Kulik, why do we bother typing f of x into the y1 spot if you didn't even use it? It's because I forgot that I did it. But that's gives me the same thing, and that's a little less typing. You guys see what I mean? Is this helpful, kind of showing you the hacks, the calculator hacks here? In particular, on the AP exam, if they ask you on a calculator section to do something like this, which sounds like a calculator question to me, like how much faster is this than writing out the areas for 6 rectangles? Or if it was 10, like Yuckarooskies, this was so fast, please do that. All right, so that's like part A. And that was what, like 3,975, is that right? Or 9,375. All right, let's do part B now. Now, yeah. So, to do this exactly, I'm going to convert this into our limit problem. Everybody's okay there? It should be, thank you. So far, so good. And we know delta x is still going to be, in this case, 3 over n. And we know that, xi is going to be 0 plus 3 over n times I, or just 3i over n. So far, so good on how I did that. I'm going to plug those things in now. So now let's see, what should I do? I'm going to pull that 3 over n out front of the summation. But notice that n is the index for the limit. So that still needs to be, and I'm going to just call this like, everybody okay there? Now I'm going to distribute my summation. And I'm going to show just like a lot of steps here. Just so that the algebra is super clear, especially the first time doing this. I'm not going to try to combine and do a bunch of stuff all at once. Once you're comfortable with this process, feel free to start doing that. But this is really the first time any of us are doing this. So I want to go slow and be really overly detailed so that it's super clear what we're doing. So I just want to let you know that not every time you do this problem does it need to be this detailed. As you get more comfortable, you can kind of do 2 or 3 or 4 things at once in a step, and that's okay. Just do what you're comfortable with. But we're going to do just one single thing at a time. All right. So now I'm going to, this is really the same thing. Well, let's do this on this step, I suppose. Let's write that as 3 cubed I cubed over n cubed. Can I do that on that step also? That seems like not a big deal to write. So I'm going to take that 3 cubed, which is 27, and the n cubed there out of the summation, because again, the summation only depends on i's. And I'm going to take that 18 over n out of the other summation, because that only depends on i's. And these two are formulas that we saw before. So now I'm going to substitute those things out using their formulas. So this was n times n plus 1 over 2 squared. And the other is n times n plus, n plus 1 or n minus 1? Shoot, I don't remember. Is it plus 1? Okay. Over 2. So far, so good. Okay. Now let's do a little bit of light combining of like terms. So I'm going to have 27 n squared n plus 1 squared over 2 n cubed minus 18 n times n plus 1 over 2n. And now I'm going to distribute that 3 over n through. Yes. Oh, thank you. Oops. That would have mattered a lot. Perfect. Great catch, Jacob. You're welcome. And then 3 times 18 is 54, isn't it? Everybody feel okay with what I've done to this point? So when I look at the numerator here, I see a degree 4 polynomial whose leading coefficient is 81. The denominator, degree 4 polynomial whose leading coefficient is 4. So what is the limit of that first piece? 81 over 4. When I look at the second piece, the numerator is a degree 2 polynomial with leading coefficient 54. The bottom is a degree 2 polynomial, leading coefficient of 2. So 54 over 2. I make a common denominator. It's 81 over 4 minus 108 over 4. So I would get negative 27 over 4, which is, I think, going to be, what is that? That's negative 3.75, right? Oh, 4 point. What? 6.75? Okay. Sounds good. Let's double check. And the textbook asked us to do this thing. Okay, that one was good. Oh, good. Yes, got it. It's always lovely when you can like jump through that much algebra by yourself and feel like, yes, no mistakes. Well, I did make a mistake, but Jacob caught it for me, which is great. Does that feel okay with what I did there? Was everybody good with the algebra that I walked through to do that? Now, that's a lot. This is the only section you're going to be doing it in. Okay? And after this, we're going to look at a better way to do this. But I think it's important that like you see like why this time saver is such a why the shortcut's such a shortcut, so you can really appreciate it. Like the derivative shortcuts made so much difference when you got away from got to stop doing the limits. The same idea will happen here. So let's do another. So it says set up an expression for that integral as a limit of sums. So, well, I know delta x is b minus a over n. xi is going to be a plus I delta x. So 1 plus 2 over n. Everybody's okay there? So my formula is the limit as n approaches infinity of the sum I equals 1 to n of f of xi. So my f is this, and my xi is that. And then times delta x, which is that. Oh, thank you. Yes. Absolutely. You're on it today. Appreciate it. And part B says use the computer algebra system to evaluate this. None of us have a computer algebra system on our calculator, I don't think, so we're not going to worry about it. Yeah, I mean, I can do it here, I think. Nope, that's not it. It's the wrong ROM. Does that one do it? Nope. All right, I can't do it either. Nope, that wasn't the one I had open. Okay. All right. It's gonna, anyways, it would be e cubed minus e to the first. There's me doing it in my head. Mr. Kulik, there's got to be a good shortcut there then, if you're able to do that in your head. There is. Okay. E cubed minus e to the first. All right. Here, we're asking you to evaluate the integrals by interpreting each in terms of areas. So what I'll do is I'm just going to kind of look at my calculator here. We'll do square root 1 minus x squared. And then I'm going to change my window to go from 0 to 1. Because those are my bounds of integration. And I'm going to hit graph. And that's pretty dumb looking. Oh, so let's just make that 0 and that 1. Try it again. What does that look like to you?
A quarter of a circle.
Quarter of a circle. I agree. What is the radius of this circle got to be? 1. So we just get pi over 4 for our area. Everybody's okay there? Classic AP exam question. They'll give you some goofy looking graph and ask you to find the integral of it. And all you get is the graph. What are you going to have to do? Chunk the thing up into geometric areas and just like compute the areas for rectangles and triangles and circles or whatever the graph is kind of composed of, just like we did here. Giselle.
Can you like redo it, another time if mine looks funky?
Oh, so I did just that.
Yeah.
And the window I did was from 0 to 1 and then 0 to 1. So I used 0 to 1 for the x's because those are the limits of integration. And then I saw something that was like Garbo-y looking. So I just changed the y's because I saw everything was between 0 and 1 there.
Gotcha.
So
like for any type of thing, put it for the y max in the y minute and then also for the x.
well, let's do the next one here.
Oh.
So this next one on my y equals is x minus 1. And then I'm going to go from 0 to 3. And I don't know what to expect here. I'm just going to reset this to negative 10 to 10, and we'll change it in a minute if we feel like we need to. So it looked like we went from negative 2 to like positive 3 or something on the y's, right? Like negative 1 to positive 2, I think. Do you guys see that? That looks pretty good.
What's stopping you from just doing like the summation limit?
Nothing.
So you could do that. How'd you know to use 1/4 pi r x squared just because it sort of looks like a circle?
Because it looked like a quarter of a circle,
Okay,
just like Elena said.
I got you.
So here, if I look at this, what does this look like?
Linear.
I say two triangles, right? I have this triangle down here that should have a negative area because it's below the x-axis, and this triangle here that should have a positive area because it's above the x-axis. Everybody okay with that? And I'll write a negative sign there. So the area for a triangle is 1/2 base times height. If I look at this triangle, the height is 1 and the base is 1. If I look at this triangle, the height is 2 and the base is 2. So we have negative 1/2 plus 2, so we get 3/2. Yes?
How would I get my computer, like, show me, like, where it, like, show, like, you know how you just said, like, it's 1-to-1? My graph doesn't show that.
Okay, so I would suggest making sure your X and Y scales are set to 1.
Oh, is that 0?
So if you set those to 1, that should put tick marks every 1 unit, and typically that's going to be, unless you're doing something trigonometric where you want like pi/2 or pi/4 or something, like
Yes.
I just almost always set my scale to 1.
Perfect.
Or we're doing something like from 0 to 10,000. It's like, well, maybe I'll set it by thousands or something so I get like 10 tick marks. But
Got it, okay.
that's what the scale does, SCL. Does this feel okay? It's just basically doing geometry. The only tricky part is you have to remember that stuff below the x-axis needs to be a negative area, right? But it's basically just using geometry formulas. So we've talked about using left-hand endpoints and right-hand endpoints. And I think even in the homework yesterday, they asked you to use a midpoint on one of the ones where they give you the graph anyways. Here's the midpoint rule or whatever. So let's do that to calculate a Riemann sum to approximate that integral. So again, we'll start with our delta x, which is 1/n, and then our xi, which should be the midpoint of that. How would I write that? Is 1/2. Oh, we'd have a plus I minus 1 delta x plus a plus I delta x. Everybody's okay there? So I'm going to have 2 a's. I'm going to have 2 delta x's and then minus 1 more delta x over 2. Right, because I just distribute that through. Okay. So my M5 is going to be 1/5 times I don't know why I did this. I don't know why I did the bother with the xi. Oh, I know why I did the xi. Because we're going to do this on our calculator. Right? And then we're just going to do the sum from 1 to 5 of 1/xi bar. That's why I wanted to do it this way. Oops, 2xi. Yes.
Can you like re-explain how you got like xi? Like, xi?
Yeah, so this is xi minus 1 is a times xi minus 1 times delta x. And then xi is a plus I times delta x. And xi bar is just the average of those two values, which is what I wrote there. What's up? A vinculum?
Yeah. The vertical or the horizontal one.
Oh. Well, that's, I think, for the, like, if you have, like, 0.3 repeating.
Okay.
I think you have to, like, that's a vinculum. I don't know if, I think that's just like a superscript or something. I don't know if that's called that also. All right. So I'm going to do 1 over 5 times, do math. We'll do summation. I'm going to use x instead of I. So x equals 1 to 5. And instead of doing like y of, I'm just going to do, well, let's go ahead and do it. It's fine. Just make that 1 over x. And I'll do vars, y vars, function y1 of, and I'm going to do the fraction, the proper fraction command. So I'll do alpha y equals, and then pick option 1. So I have a is 1, so 2a is just 2 times 1, or 2. And then plus 2i, instead of I, I'm putting x's. And then times our delta x, which is 1 over 5. And then we have minus another delta x, so minus 1 over 5. And all of that was over 2.
Oh, that'd be like.
Well, I did the y1.
Oh.
I put it in there, so I decided, I was like, whatever. So I get there 0.6910, yada, yada, yada. Everybody's okay with that? Yeah, this was asking to use the midpoint rule, which was the stuff right above us. Absolutely. Yes, of course. Sorry. So I think between the line above and the line that's there, Giselle, you can see the whole thing,
Yes. So
right?
it's
So that's,
y1 times 2.
well, that's of,
Oh, yeah.
and that thing that it's of is just my xi, right?
Yeah. So 2 times 1 plus 2 times 1 over 5.
Yes. Because 1 over 5 is delta x.
Yeah. Got it.
Uh-huh. Okay. Now, properties of our definite integral. So these are things that we can do to like rearrange our definite integral to make the problem easier. So the first one, if I flip the bounds of integration, the integral just becomes negative. So if we're going from b to a and we switch it to go from a to b, we just negate what we're doing. Is everybody okay with that? We'll see some examples here in a bit. Okay, but just these are things you can do. Trivially, if we're going from a to a, the area under the curve should be 0 because you have a rectangle with width 0. You're subdividing 0 as the width. So if I do the integral of a constant, well, that should just be a rectangle because you have a horizontal line, right? Where the height of our rectangle is just c. And then the width of our rectangle is just the interval from a to b. So the distance from a to b is b minus a, so that's just a rectangle. You can distribute integration across a sum or difference. Right, that's what properties 2 and 4 are saying. And then property 3 says I can pull a constant out front of my integral and just do the integral of f of x dx and then multiply it by c when I'm done. What do these all look a lot like? The summation properties, right? Why do they look like the summation properties? Because an integral is really just an infinite sum, right? Yeah, like the natural log and exponent properties look similar because they are kind of related to one another. Sure. Is everybody okay with that idea? So again, nothing super surprising there, I would hope. So it says use the properties of integrals to evaluate this one. So I would say first things we would do is distribute our integral. The next thing is that first integral is an integral of a constant. So that's going to be 4 times 1 minus 0. The second integral is I can pull the 3 out front. And then this piece, I'd have to use my definition and the summation properties to get to, right? Limit as n approaches infinity, the sum from 1 to n. My xi is just I over n. And my delta n, or delta x is 1 over n also. So there I'm going to take the n's out front of the sum. And then I know that my sum is n plus 1, 2n plus 1 over 6. That's one of our summation formulas from before. I notice this limit, I have a degree 3 numerator, or degree 3 polynomial in the numerator with leading coefficient 2, and a degree 3 polynomial in the denominator with leading coefficient 6. So that limit should be 1/3. Is everybody okay with that idea? The next property we're going to see should be intuitive because we've already kind of used it when we did that geometry problem we broke the integral up into 2 triangles. Well, this just says that the integral from a to b is equal to the integral from a to c plus the integral from c to b, which is exactly what we did with the triangle problem, where we went from 0 to 1 and then 1 to 3. So like you can break an integral apart into two pieces as long as like the end of one integral is the start of the next integral. Does that feel okay there? Again, very natural because we've already did this. We already did this intuitively. Like, oh, if I want to calculate the area of this thing, I can just do like this area plus that area and the area of the whole thing. Same idea here. And I think this is this is a never-ending section. All right. So what we want to do here is it asks us to solve for the integral from 8 to 10 of f of x dx. So I know that the integral from 0 to 10 of f of x dx is equal to the integral from 0 to 8 f of x dx plus the integral from 8 to 10 of f of x dx. Using that previous property, tells us that that first integral is 17, that this next integral is 12, and so what does this integral have to be? Five. And I'm done. Like the easiest algebra you've ever done, right? Does that make sense as to what I did there? Again, just using that property. And Isabel, this is a problem where very possibly they would go from like 10 to 8 here. So you'd have to use that flipperoo property that you asked me. When would I ever use that? On a problem like this, very often. Just not in this specific example. All right, our last idea says that, if f of x is always positive over some interval, its integral has to be positive. Well, no doy. If f of x is always bigger than g of x, well, the integral of f of x always has to be bigger than the integral of g of x. All right, no doy. If little m is some lower bound for f of x and capital M is some upper bound for f of x, then the rectangle formed with the lower bound is a lower bound for the integral of f of x. And the rectangle formed by the upper bound of f of x will be an upper bound for the integral of f of x. And we would use that last property to do that last example, but we're out of time here. This is the homework set. The boldies are the ones that I would be asking about as a homework quiz problem.
Real quick. How'd you know which one was A, B, and C for the integral points?
Well, I just was breaking up 0 to 10 to 0 to 8 and then 8 to 10.
Okay.
Because it gave me 0 to 10, gave me 0 to 8, and wanted to know about 8 to 10.
Right. Okay.
So I go 0 to 10. Is that the same thing as going from 0 to 8 and then 8 to 10?
Okay.
And I didn't worry about the A, B's, and C's. I just like the end of one integral needs to be the start of the next integral.
Right. Okay.
That's
so
all
it's like 0 to 10 encompasses all of it. Okay.
Yeah.
Okay, I got you.
Does that make sense?
Yeah, that's good.
So it's just like
You want to add the ones together that the sum of those, like of the integral points minus each other equals like the.
you just want to. It's just like a segment. If I go from like 8 to 10 and then or 0 to 8 and then 8 to 10, that's the same thing as going from 0 to 10.
So
Like you
it's
just need to hook it
8
together.
+2. I got you. All right, thank you.
You too.